So, good afternoon, hey everyone. Lecture 29. We're talking about compressible flow today, about compressible flow regimes, the speed of sound in an ideal gas, and the Mach number. So, let's get started. All right, so here's an overview of what we're talking about today. It covers sections 11.3 and 11.4 in the textbook. All right, so the Mach number, I'm sure you've heard of it. It's sort of one of the fluid dynamics concepts that makes it out into popular culture. Mach number is simply defined as the ratio of the flow of a fluid, the speed of the flow of a fluid over the speed of sound in that same fluid. We're going to be deriving an expression for the speed of sound in an ideal gas today. And there's a rule of thumb, like we have these different rules of thumb for Reynolds number and when a flow is turbulent. We have a rule of thumb for when a flow can be considered compressible or incompressible. So it turns out that if your Mach number is less than about 0.3, you can consider the flow to be incompressible. So let me write that with a wiggly equals here. And then if your Mach number goes above 0.3, you have to start worrying about compressibility effects. So when we're thinking about this, if we think about phenomena like sonic booms, hypersonic versus subsonic flow, it all has to do with sound waves in air, right? So what we perceive as sound is just these weak pressure pulses as depicted in the figure here. You can see that they're longitudinal waves, right? And they hit the eardrum, and our eardrum responds to it with really high precision, right? So we can distinguish between really, really subtle differences in a sound pressure signal. We know when it's a dog barking versus a cat meowing. And so we've really evolved to very good discriminators when it comes to discriminating between sound signals. And then down on the bottom here, you have just the amplitude versus time of the pressure wave. All right, but we want to derive an expression for the speed of sound. We did this not too long ago for the speed of a wave on top of the surface of the water when we were talking about open channel flow. This is the same idea, but now we're talking about how far does a pressure disturbance travel in air or another ideal gas, how fast, right? So to think about this, we'll imagine an infinitesimally thin, weak pressure pulse moving through a fluid at rest. So let's imagine that we produce this by snapping our fingers and it just sends one pressure wave traversing the room, okay? So if we imagine our control volume is moving with the wave, we see the picture on the left. And then if we imagine that the observer is moving with the control volume, we have the situation on the right. right? So here's the control volume from the frame of reference of an observer moving with a control volume surrounding the wave. It looks like the wave, this pressure pulse, is still, and we've got fluid coming up behind it with a velocity c, which is actually the speed the wave is moving at. And then to the right, we see a velocity c minus delta v, right? And that's because as the wave propagates, it sets into motion the air around it. And so on the left of the wave, we've got some pressure, density, and speed and of the air. And on the right, we've got P plus delta P, rho plus delta rho, C minus delta V, right? And then we've got a cross-sectional area for the frontal projection of our control volume. So we can apply the continuity equation to the left and right sides of this control volume when we get rho Don't do this to me again. PDF annotator just sent me a message that it's not responding. So we're going to try once restarting it, and hopefully that'll work. So I got a lot of stuff that I'm excited to share with you today. Okay, it's restarted. Let me just open my file back up, and hopefully we'll be good to go. Fingers crossed. Looks like it's doing okay. Okay, here we go. Sorry about that. So applying the continuity equation, we have rho AC equals, on the left, equals rho plus delta rho AC minus delta V on the right. This is equation 1135 in the textbook. Or rearranging this, we've got rho C equals rho C minus rho delta V plus C delta rho minus delta rho delta V. And you can probably guess where this is going, right? We've got delta times delta, this higher order term here, and we are indeed going to say that it's negligible in magnitude compared to the other terms. All right, and we do that, and we've got now rho delta V equals C delta rho. All right. My PDF annotator just quit on me again. I really want to teach this class today. I am going to try this one more time and cross my fingers, although I'm not hopeful. Just give me one moment to try this again. And if it doesn't work for us, then I will have to record this class and upload it, but I hope it doesn't come to that. If it does come to that, bear with me because I want to show you a video about sonic boom before we go. Come on, annotator, I know you can do it. You got this. Okay. So we neglect the higher order term. We end up with rho dV equals C d rho. This is equation 1137. We've applied conservation of mass. Now let's apply conservation of linear momentum. We get minus C rho Ca plus C minus dV times rho plus d rho times C minus dV A. So those terms I just wrote down are the flux of momentum through the control surface. And now on the right, we've got the sum of the forces acting on the control surface. We've got the pressure force acting on the left, and we're subtracting from it now the pressure force acting on the right of the control surface. All right, so we're neglecting friction forces in that expression, right? As you can see, we only wrote down pressure forces on the right-hand side. If we now neglect those higher order terms, we end up with minus C rho Ca plus C minus delta V rho AC equals minus delta PA. Or rearranging, we've got rho delta V equals delta P over C. This equation 1139, and here we're combining 35 and 38. All right, and then from 37 and 39, we get C squared is delta P over delta rho, or rearranging, we have our expression for the speed of sound. Delta P over delta rho. This is 1140. If we now assume that the flow is adiabatic, there's no heat transfer in, since we're already talking about an ideal gas, the flow is isentropic. Since we're already talking about a frictionless flow of an ideal gas, the flow is isentropic. And then in the limit, as delta P, delta rho go to 0, we get the following expression. Right, so what's different here is that the deltas change to del's partial derivatives. And the subscript S here means that the differentiation is occurring with the entropy being held constant. All right, now if you remember the bulk modulus from chapter 1, it's a measure of compressibility in any fluid. Doesn't matter if it's a gas or a liquid. And it's defined in the following way. It's dP over d rho over rho, or rewriting that, it's rho times del P, del rho with constant entropy. All right, so in general, we have the following expression. If we use 43 and 44. All right, so in general, we've got that the speed of sound in a fluid, whether it's a liquid or a solid, is the bulk square root of the bulk modulus over the density. So what does that give us? If we look at the figure on the top right here, we can see the speed of sound versus the temperature. And you see that for both air and water, the speed of sound varies a little bit and increases a little bit with temperature. And the physical reason behind that is that the higher the temperature, the more the particles making up the fluid are bouncing around and colliding with each other. And so any signal is passed through the fluid faster. But it's really interesting to note, maybe a little counterintuitively, the speed of sound through water is much higher than the speed of sound through air. It's kind of funny, you know, if you've ever been underwater in a pool and somebody talks, you can hear sounds, but they sound like they're really slowed down. They're actually much faster. And that makes sense intuitively from a physics perspective, right? Because water molecules are much more densely packed than air molecules, right? So if you have a really small intermolecular distance, you can easily collide with molecules next to you and pass along a pressure wave or a pressure signal. When the molecules are farther apart, like they are in a gas, the sound signal, the pressure signal, travels slower. All right, last time we derived the following expression for an isentropic flow of an ideal gas. It was that P is a constant times rho to the K power, where K is the ratio of specific heats, Cp over Cv. And if you remember, for air, K is 1.4. So we can express our partial derivative like this. It's some constant times K. Now all we're doing is differentiating this expression up here, equation 1127, right? When we differentiate it, we get K rho to the K minus 1 power. Now, what if we just use this equation here, rearrange it, and solve for the constant? It's just P over rho to the K. So we're going to plug that in for the constant times K rho to the K minus 1. And we end up by invoking the ideal gas law. Let me actually do one more step of this so it becomes a little clearer, right? So this simplifies to K P over rho, but then by the ideal gas law, this is K RT. Right? So for an ideal gas, the speed of sound is the square root of K RT. This is super important. We're going to box this in red. Equation 1147. All right. So another thing to note, if you look at the figure on the bottom right here, this is the value of K, that ratio of specific heats for a couple different ideal gases. So air and hydrogen have approximately the same value of K, but then helium has that higher K value. So that explains the helium balloon effect, right? If you look at the speed of sound in a gas, it's proportional. It increases with increasing K. So helium has a higher K value. So when you take helium into your lungs, which you shouldn't do, it's dangerous. But when you take helium into your lungs and then speak, that's why it's so hilarious, right? It sounds sped up, and it in fact is. The sound is traveling faster to your ear when helium is the medium it's traveling through rather than air. All right, we can also rewrite our thermodynamics formulas in terms of the Mach number. So if we take our Mach number and square it, it gives us just V over C squared, right? But we just wrote down an expression for C for an ideal gas. So this becomes V squared over K RT, following the expression we wrote down on the end of the last page. Now, using the ideal gas law, we get rho V squared over K P, just plugging in the ideal gas law there. This is equation 1148 in your textbook. We can now take that and substitute this expression into those ratios that we derived last time. If you remember, we derived the ratio of the stagnation to static pressure, temperature, and density, right? Our thermodynamic quantities. And they weren't in terms of the Mach number, they were in terms of velocity and the specific heat, C sub P, right? Well, we can actually replace that term and rewrite those equations using this expression here, and we get the following. So our ratio of its stagnation temperature to static temperature for an isentropic flow of an ideal gas is 1 plus k minus 1 over 2 times the Mach number squared. And this is 1150. We have a very similar relationship for the ratio of the stagnation to static pressure. And it is 1 plus k minus 1 over 2 times the Mach number squared, but now raised to the k over k minus 1 power. This is equation 1151 in your textbook. And then finally, we've got the ratio of stagnation density to static density, 1 plus k minus 1 over 2, Mach number squared, 1 over k minus 1. And this is 1152 in the textbook. So these are handy, and when you're dealing with an ideal gas that's not air or doesn't have a ratio of specific heats K that's equal to 1.4, like we see here, then you need to use these. But they're a little unwieldy, so it's a lot easier if instead of using these formulas, you use the tables and plots in Appendix D. So there's figure D1, which is the first thing in Appendix D, and it plots these ratios as a function of Mach number. And then they're tabulated in the next item, which is table D1, right? So if you're dealing with air or another ideal gas that has the same K, 1.4, just go to Appendix D. It's a lot easier. You may have to do linear interpolation if you're between two Mach number values, but it's simpler usually than using the formula. If you're given a K value and it's not 1.4, then you do have to use these formulas. And I just want to draw your attention here to, if we plot these equations versus Mach number, right? So here we've got this equation, here we've got this one, and here we've got this one plotted. Look what happens if you've got a low Mach number 0. Remember, by our rule of thumb that we talked about on the first slide, if you've got a Mach number less than about 0.3, you can consider your flow to be incompressible, right? So properties, thermodynamic properties don't change much. So you see that here, right? So Mach number of 0.3 is maybe, here somewhere on these plots. And you can see that these ratios, these quantities are all basically constant up until a Mach number of 0.3, and then they drop off drastically with Mach number, right, as you increase the flow speed. And so when you get to a Mach number of 1, which is considered sonic flow, it's still holding pretty steady. Maybe you've got a ratio that's, we've lost maybe 30%, but then when the flow becomes supersonic, above a Mach number of 1, these quantities just drop off drastically, and the behavior, the thermodynamic behavior is completely different, right? And so you can no longer use relationships that assume that incompressible flow. All right. So here I put this in big and bold just so, to remind you. So if you're dealing with A, just use the appendix. All right, so talked about Appendix D. Here is that first figure from the appendix. So here you've got, on the horizontal axis, you've got the Mach number. On the right vertical axis, you've got a ratio of areas, and this is something for converging, diverging duct that is beyond the scope of this class. We're not going to talk about it. If you're curious, you can read the later sections in chapter 11, but it's beyond the scope of this course. But then here on the left vertical axis, you've got your stagnation ratios. Notice they're flipped, right? So we've got static over stagnation pressure, temperature, and density. Whereas on the previous page, we had the T naught on top. In this figure, it's flipped. T naught is on the bottom, okay? So then you've got We ignore this curve. This is A over A star, but we've got our T over T naught curve here, our rho over rho naught curve here, and then our P over P naught curve. So if you're given a Mach number, say it's Mach 1, you just trace it up to which is the appropriate curve, whatever quantity you're looking for, see where it intersects, and then trace that back to the vertical axis. Okay, so that's how you use that. If you want to be a little bit more precise numerically, you might want to use table D1 instead, which is the next item in the appendix D. And it's got the same thing. It's got the Mach number in the first column, and then it's got the ratio of static to stagnation temperature, pressure, and density in the next three columns. The thing here is it's not continuous, right? So if you're given a Mach number that falls somewhere in between these values, you can either, not be terribly precise and pick the nearest value, or if you want to be more precise, you can interpolate using linear interpolation. Again, keep in mind this is for K equals 1.4, so air, or maybe a problem would say something like an ideal gas with K equals 1.4, right, without specifying that it's air. All right, so let's go into an example. This was example 2 from last time that we didn't quite have time to get into, but let's do it today. So here we've got the air flow through a duct, and we're seeing the flow from the side. We're told that the velocity of the airflow is 750 feet per second, and the static temperature is 100 degrees Fahrenheit. So what's implicit in the way that this problem is stated is that we're assuming it's uniform flow, right? Because it just says the static temperature and the static velocity, right? So really we're assuming uniform flow. So none of these properties are changing with elevation within the duct. Okay. And then we've got a little pitot tube in there, right? And so if we follow a fluid streamline from point 1 here, let's call this 1, to point 2, at point 1, we're going to have the static properties, and at point 2, we're going to have the stagnation properties, right? So here at 1, we've got P, T, V. I'm not going to give them subscripts. And over here, we've got P naught, T naught, and then of course, V naught is identically equal to 0. The stagnation velocity is 0 by definition, okay? All right, so we've got our static properties over here at 1 and our stagnation properties inside the pitot tube where the fluid comes to rest along that stagnation streamline where it hits the wall. And then down here, we've got a mercury manometer, right? And it's showing a height differential of 8 inches. And the question is, use the manometer measurement shown to calculate the static and stagnation pressures of the flowing air. Right, so we're given static velocity and temperature, and that's all we're given. And then we're given the differential temperature reading here. All right, well, it's uniform flow. So we know that the pressure here is just the hydrostatic pressure. So we're going to apply the manometer equation. For the manometer rule, which tells us that the static pressure is equal to stagnation pressure plus the difference in heights. But now our manometer fluid is mercury, right? So we have to be careful about that. Okay, so we do that and we get this expression, P naught minus P is equal to 8 inches of mercury, and then we've got our conversion factor. So 1 pound per square inch is equal to 2.036 inches of mercury. So this gives us 3.93 psia. And we'll call that equation 1. Now we want to use these tables, this table D1 that we just talked about in Appendix D, right? So why? Because we know that we have the flow of an ideal gas, air. We're going to assume it's an isentropic flow, no problem, because we've already seen that we're assuming it's a uniform velocity. That means there's no friction. So it's frictionless, there's no heat added, it's adiabatic, therefore it's isentropic. Its entropy doesn't change. Okay, so the fluid Mach number is just, by definition, V over C, but of course we just derived an expression for C in an ideal gas. It's root KRT. So here we've got 750 feet per second over 49.02 times the square root of 100 plus 460 feet per second. So what's happening now with the 49.02? That is the factor that we get when we take K and R for air and we take the square root of them. It just pulls out and it gives us 49.02. So then all we're left with is the temperature. And of course, we have to convert always, right, with these compressible flow equations, we have to convert from static temperature as it's given to an absolute temperature, right? So to get degrees Rankine, or to get Rankine, we have to add that 460 to our Fahrenheit measurement. So we get 100 plus 460 to give us 560 Rankine, which is equivalent to 100 degrees Fahrenheit. All right, and this gives us 0.647 for our Mach number for this flow. So let's just take a moment and think about that 0.647. If we think about our rule of thumb that we have to worry about compressibility effects after a Mach number of about 0.3, we're sort of double there, right? We're sort of at double 0.3. But we're still subsonic. So we're not at a Mach number of 1 where the flow speed is equal to the speed of sound. We're still in a subsonic flow regime. Okay, now we can go to table D1. And what we see in table D1 is that, well, we don't have an entry for a Mach number of 0.647. We have an entry for 0.6 and 0.65. So if we interpolate, we get that P over P naught is equal to 0.7547 for the Mach number 0.647. And let's call this equation 2. All right, so now we have two equations for our two unknowns. One unknown is P, the static pressure. The other unknown is P naught, the stagnation pressure. We can solve those together. We can rearrange equation 2 and plug it into equation 1 first. So what we find is that P naught is equal to 16.02 psia, and P is equal to 12.09 psia. Does anyone remember what that little A at the end of psi stands for? Absolute. Yeah, that's right, Leah. Thank you. So it stands for absolute, and that means that we're dealing with absolute pressures, not gauge pressures. Right? So we're including atmospheric pressure. All right, I'm afraid to hit save on my notes here because I'm afraid it'll crash it. So I'll wait until the end to do that. So here we see we've got a stagnation pressure here inside our pitot tube, and it's higher than our static pressure. And that's exactly what we expect, right? So by the Bernoulli equation, we expect that if the velocity is decreased, brought to zero, we're going to see an increase in the pressure. And those trends hold for compressible flows as well, at least subsonic compressible flows. So let's talk now about compressible flow regimes. So here we've got an example, which is the airflow over a sphere. And this actually references your last homework problem on this week's homework, homework 12. We didn't cover external flows in this class. It's beyond the scope of the course. You'll have that in fluids 2 if you take fluids 2, depending on your major. But for external flows, we calculate the drag force on an object, F sub D, by using the dynamic pressure times the area times something called a drag coefficient. So basically, if you've got air flowing, with speed V, and you've got something with a projected frontal area of A, how much drag force that object experiences depends on its drag coefficient. And the coefficient changes a lot with the shape, right? Whether it's a circular cylinder, a sphere, a cube, right? In general, the smoother and more aerodynamic an object is, the lower the drag coefficient that it has. Well, here, looking at this figure over on the right, we've got on the vertical axis this drag coefficient, and on the horizontal axis, we've got the Reynolds number, and you can think of the Reynolds number again as just a normalized velocity, right? So this is really slow flow speed up to really fast flow speed. And then these 4 different curves we're looking at are different Mach numbers, right? So here we've got a Mach number of 0.3. This is just barely starting to take into account compressibility, right? Because Mach number less than 0.3 is basically incompressible flow. So let's say that for an incompressible flow of air around the sphere, this is what the drag coefficient looks like with speed. As you increase the speed, the drag coefficient drops drastically. Well, then if you increase the Mach number, and now we're looking at Mach number of 0.6, so still subsonic, but we're definitely into the compressible flow regime, that sort of stretches this curve out, right? And you get the same spot here that we did at a Reynolds number of 4 times 10 to the 5th, we get it over here at 8 times 10 to the 5th, right? And then as we increase our Mach number, we're just almost sonic, and then here at the very top we're sonic, amazingly, the drag coefficient doesn't change with speed. It becomes basically a constant with speed. So we can get really, really drastic changes in behavior when the flow becomes compressible. Some of the really famous examples that we won't be able to cover in the course, they're beyond the scope of the course, but you can get things like if you have a sonic or supersonic flow, you can have a flow that accelerates as a duct cross-sectional area increases. So let's say you have a converging, diverging duct or nozzle, and you have flow speed that comes in subsonically, and then at the throat, at the minimum cross-sectional area, it reaches a Mach number of 1. Now, as it flows through the duct and the duct cross-sectional area gets larger and larger, the flow actually speeds up instead of slowing down, right? So normally our intuition from the continuity equation is if the diameter gets smaller, the flow speeds up, and vice versa. Once you have a supersonic flow, that's not necessarily true. So that's one really counterintuitive result from compressible flows, but it's beyond the scope of the course. Another thing that can happen for compressible flows is you can actually get flow speeding up when you increase friction, right? So another really counterintuitive thing beyond the scope of the course. All right, last slide here before we hopefully will have time for a movie. If not, you can watch it on your own. Movie about sort of sonic booms that relates to the aircraft, the NASA aircraft, Lockheed Martin aircraft I've got behind me. All right, so now I want you to imagine that you've got some object and it's traveling from right to left with some speed v. And it's emitting a sound once a second. So let's say a beep, right? And that sound is just moving away from the object in a circular wave with a constant speed. So here, if our object's speed v is 0, the objects just sit there. The object is denoted by this red star, this red asterisk. It just sits there, and these sound waves just move away from it in a symmetric way. Here's this larger diameter wave is the one that was made 3 seconds ago. This next smallest one, right, here's 3 seconds ago. All right. So annotator just quit on us again. But hopefully you've got the slides open in front of you. Let me try one more time restarting it because this is annoying. I, of course, lost all my annotations I did because I was afraid to hit save because that seemed to be crashing it before. Ooh, it's letting me restore it. How generous. Oh, wonderful. Kept all the annotations. Hallelujah. Okay, here we are. Wonderful. Thanks for bearing with me. Okay, so here, our object, denoted by the red asterisks, is not moving, and these sound waves are moving out. The largest radius one. Oh, I'm not sharing. Sorry about that. Hold on. Screen share. You can do it. Yes. Okay. Everybody see that? Good. Okay, V equals 0. Largest circle here was a sound wave emitted 3 seconds ago. 2 seconds ago was the next largest, and then this one was emitted 1 second ago, right? Here, we've got some non-zero velocity, but it's still lower than the speed of sound in air, okay? Or if you're imagining the analogy of ripples on the surface of the water, then that would be the speed of the water waves on the surface of the water, right? So here, the object is moving to the left as it's emitting these sounds. So they're sort of piling up near the front. We've got really close distances between the ridges of these sound waves. And in the back, they're getting farther and farther apart. These are both subsonic cases. Here we get to our critical sonic case, where our Mach number is equal to 1, right? Because V is equal to C. And we get to the point where these waves, ridges, the peaks come and they meet and they pile up at the same location. And this is the phenomenon that leads to a shock wave. Okay, when you get a bunch of sound waves piling up, happening at the same location, in perfect analogy to our hydraulic jump when we were looking at channel flow and the Froude number being critical and those surface waves piling up at the same location. Here, we've got these sound waves piling up at the same location. Then we move over into our final case, we're supersonic, and we're actually moving at a speed which is greater than the speed of sound in our fluid. And what happens then is these sound disturbances cannot travel outside of this so-called Mach cone, this cone of silence denoted by the red dashed line. So there can be no information transfer forward. And what that means is there is a discontinuity in many fluid properties before this line and behind it. So if you imagine traveling through this shock wave, you experience a sudden change in pressure, density, and temperature. So we have a comment about getting confused about the downstream and upstream exact locations. And so I think that brings me to my next point. So upstream in this case is here in front of the cone, and downstream is here. And we can actually say geometrically what the angle of this cone is. It turns out that this cone is defined by this angle alpha, and that sine of alpha, we can show it's just 1 over the Mach number, right? So here on the bottom right, we have a really interesting thing. We've got flow through a compressor, and the air is compressed here by having a supersonic flow enter bottom left and exit at top right. And it passes over a series of compressive fins that create shock waves. So it enters at really high speed on the bottom left, passes through a shock, loses speed, loses energy due to friction from passing through that shock. So it's a little bit decelerated. Then it passes over the next compressor here, and it goes through a second shock wave, loses a little more speed, third compressor fin, third shock wave, et cetera, et cetera. By the time it exits the compressor, it's subsonic. Right? And this is actually a really beautiful example of Schlering imaging, which is what the extra credit discussion question is about for this week's module. It's this shadow graph formed by differences in density that cast shadows when they're illuminated with light. All right, so last thing I want to talk about is to write down the different compressible flow regimes. So we've got incompressible flow. And the rule of thumb there is that the Mach number is less than about 0.3. Then we've got compressible but subsonic. And that's between 0.3, and 1. Then we've got compressible supersonic. And that's for a Mach number greater than 1 or equal to 1. And then a couple more regimes I want to mention. Transonic, if you remember, we've got transitional pipe flow between laminar and turbulent, right? And that's from a Reynolds number about 2,000 to 4,000 roughly. Here, between Mach numbers 0.9 and 1.2, that's considered transonic. And of course, Mach number equals 1 is exactly sonic. And then finally, we've got hypersonic flow. And that's a Mach number greater than about 5. And so if, modern aircraft traveling at really high speeds, they have transonic flow over parts of their bodies, right? An aircraft, a spacecraft re-entering the Earth's atmosphere would reach hypersonic speeds, right? Where you have, really extreme shock waves. And let me just take a moment now to talk about the aircraft behind me in my background here. It's a Lockheed Martin X-59 Quest aircraft, and it's quiet supersonic technology, and it's part of NASA's low boom project where they want to achieve supersonic flight, but without the really disturbing sonic boom that people complain about, right? So that's this aircraft. And one thing that I want you to notice about it is you can see that the wings are swept backwards, right? And so if you're an aircraft buff and you're really into modern aircraft, aircraft that are designed to fly supersonically have to have wings that are swept back. And the reason is this Mach cone, this cone of silence here, right? So if you've got an aircraft body here, if you have a standard aircraft with wings like this, they will go through the shock wave and cause lots of damage, right? And it'll be hard to achieve the kind of flow that you want. So aircraft that are designed to flow supersonically have swept back wings, like the one that we see here, and that's it so that they can stay inside that Mach cone. All right. Oh, and I'm over time. I'm so sorry. I didn't realize that. You can watch this video on your own, and midterm 2 grades are up. So please email me and Hyungan if you have any questions about that. And I want to leave you with just the score distribution on the midterm. As you can see, the scores are much more spread out this time than they were last time. I will take any questions that you have.